Have you ever just stopped and wondered how a computer, a machine that literally runs on tiny, fleeting pulses of electricity, can remember anything at all? Well, let's pull back the curtain and look at the engineering magic that makes it all possible. I mean, think about it. It seems kind of impossible, right? An electrical signal is there 1 second and gone the next. So how in the world does your phone remember your password? Or your computer keep your document open? The answer is pretty amazing. It's all about circuits that are cleverly designed to catch and hold on to those pulses. The secret sauce is something called a clocked sequential circuit. Okay, that sounds super technical, I know, but the key words are clocked and sequential. Clocked just means everything happens in sync, to a steady beat, like a metronome for the computer. And sequential means it has these special memory bits that let it remember what happened in the past. This is the basic idea behind all digital memory. And at the very heart of all that memory is this tiny little component, the flip-flop. Honestly, the best way to think about it is like a microscopic light switch. It can be on or it can be off, a 1 or a 0. That's it. It is the absolute smallest piece of memory possible, holding just one single bit. But from this one simple switch, we can build everything. So how do we get from storing just one single bit to something useful, like a number or a character? It's actually really simple. We just group these little flip-flops together. If we line up 4 of them side by side, we create what's called a 4-bit register. And just like that, we've built our first small but very real piece of memory. And that thing we just built, that's our first key component, the register. Its whole job in life is to hold a piece of digital information. You can think of it like a tiny digital notepad, where the computer can jot down a number and just hold it there until it needs it again. Okay, so our register can hold information. That's great. But this brings up a really critical new problem. We can't have it just constantly updating with whatever new data flows by. We need precise control. We have to be able to tell it, okay, hold on to what you've got, and now grab this new piece of info. So how do we get that control? The solution is a really smart control signal called a parallel load. You can literally think of it as a gatekeeper. When the load signal is off, the gate is down, and the register just keeps holding its current value, totally ignoring anything new. But the moment we switch load on, the gate opens up, and on the very next tick of that system clock, bam, the new data gets loaded in. It gives us perfect moment-to-moment control. So, storing information is one thing, but a computer's real power comes from moving that information around and processing it. And to do that, you need another building block. This brings us to the shift register. A shift register is a special kind of register. It doesn't just hold on to its bits, it can move them. With every single tick of the clock, every bit inside that register scoots over one position in a perfectly synchronized little parade. A bucket brigade is the absolute perfect way to picture this. Seriously, imagine each flip-flop is a person standing in a line. And on command, that's the clock pulse, each person passes their bucket of data, their bit, to the very next person in line, all at the exact same time. And right there, this ability to move bits one by one, serially, versus loading them all at once, in parallel, introduces one of the most fundamental trade-offs in all of computer engineering. It really boils down to a classic question. Do you want speed or do you want efficiency? Here is that trade-off in a nutshell. A parallel approach is way faster. You move all your data in one big gulp. But it costs you more in hardware. You need more wires, more logic gates. The serial approach, on the other hand, is slower since you're just moving one bit at a time. But it's so much cheaper and simpler to build. This is the classic engineering dilemma. Do you want it fast or do you want it simple and efficient? Okay, so we can store data with registers, and we can move it with shift registers. But how does a computer keep track of what it's supposed to do next? How does it control the sequence of operations? For that, we need another special component called a counter. Right, so the crucial thing to get here is that a counter isn't really for storing random data. Its entire job is to step through a very specific pre-programmed sequence of numbers. 0, 1, 2, 3, 4. It generates the timing signals that act as the master controller for everything else happening in the system. But wait, if a counter is made out of the same flip-flops as a regular register, how do they all coordinate to actually count in the right order? Well, it turns out there are 2 very different ways to get this done, almost like 2 competing design philosophies. And these 2 methods are called the ripple counter and the synchronous counter. The way they work is fundamentally different, and that difference has huge consequences for how fast and reliable they are. Okay, let's break this down, because the difference is really cool. A ripple counter is just like a line of dominoes. The first flip-flop changes, and that change knocks over the second one, which then knocks over the third one, and so on. It's a chain reaction. Now, a synchronous counter is the complete opposite. All the flip-flops are wired up to the same master clock. They're like an orchestra, and the clock is the conductor, telling everyone to change their state at the exact same instant. Now, that domino effect in ripple counters, it sounds neat, but it creates a massive problem. Each domino takes a tiny, tiny fraction of a second to fall. We call that a propagation delay. And as you add more and more bits, those tiny delays add up. The signal ripples through the circuit, making it slow and, at high speeds, completely unreliable. You just can't build a modern computer on something that might get its timing wrong. And this is exactly why synchronous counters are the industry standard. Because every single component is listening to the same conductor, that system clock, their operation is perfectly predictable and totally reliable, no matter how complicated they get. Everything happens in perfect lockstep, which is absolutely essential for the kind of high-speed digital systems we use every single day. So let's just do a quick recap. We have registers for storage, that's our digital scratchpad. We have shift registers for movement, the bucket brigade for our bits. And finally, we have counters for sequencing, the master metronome that controls the whole show. 3 simple building blocks, but they are incredibly powerful. Which leaves us with a final thought. We started with a simple switch that can be a 0 or a 1. And from that, we've built circuits that can store information, move it around, and control the timing of everything. If these are the fundamental components, the digital Lego bricks of our world, what can't you build?